Good evening students, this is Tuhin sir again, and we are continuing with friction, but we are going to deviate a little. Anyway, there will be a playlist in front of you, so all the friction related videos will be in one playlist. We have in front of us an almirah which is about usually around 5 to 6 feet, and if one were to try to push the almirah or even pull it, he could do it with his hands horizontal to the ground without making an angle with the ground. So here it is pushing the almirah towards the right, here he is pulling it. Supposing there is a latch or something and he is pulling it. In both cases, the friction force exerted by the floor on the almirah will be the same, and there will be no difference in the force that the man has to exert in either pushing or pulling the almirah. In real life, however, we often deal with situations, in fact in daily life situations, where we have to pull or push objects which are just about maybe a maximum of 2 feet, like trolley bags which millions of people use on a daily basis when he or she is traveling to the airport or the bus station or the railway station. You don't expect a person to kneel down or to bend and then keep his hands horizontal so as to push the or pull the trolley bag. So what does he do? Typically, he either pulls it, making an angle theta with the horizontal, or he pushes it with the same force, again making an angle theta with the horizontal. So in the first case he is pulling the trolley bag, in the second case he is pushing the trolley bag, and in this video will be titled "Pulling is easier than pushing." Now why is that? Before we go into pulling and pushing, let us take a scenario in which there is a mass of M and a man is being asked to pull it. mg acts downward as usual. Now supposing somebody were to push this particular object vertically downward with some force F dash, would it become more difficult for the man to pull it when that external force F dash acts vertically down on the body? Yes, you are right. The answer is yes. So why is that? Because now the total force acting on the body vertically downwards is mg plus F dash, and the normal force exerted by the surface on the body will be equal to this, and therefore friction force will increase, and friction force would become mu s, and mu s is the coefficient of static friction, into mg plus F dash. Instead of just mu s mg, so you will have to exert a greater force in order to pull the same object if a force F dash acts vertically downwards. Now taking this forward, first let us go to the case of pulling. So there is a body of mass m. It is being pulled by some external force F, making an angle theta with the horizontal. Since this is mass m, so mg acts vertically downward as usual. This F can be broken up into components F cos theta, which causes the body to move towards the right, F sin theta acting vertically upward. Now when you pull this trolley bag, if you were to lift it from the ground, then the body is going to lose contact with the ground. So you cannot lift it. If you are lifting it from the ground, then the upward force, net upward force will be greater than the net downward force. So the trolley bag has to be in contact with the ground in order for friction to even work. So normal force in this case will be, because there is a vertical equilibrium and vertical axis I am taking as the y-axis. So what are the forces upward? The forces upward are n plus f sin theta. That will be in equilibrium with the force downward. In this case, the only force downward is mg. So normal force becomes mg minus f sin theta, and friction force will become mu s mg minus f sin theta. This I called as equation 1. On the other hand, if I were to push this body with the same force, making the same angle theta with the horizontal, so this force F can now be resolved into F sin theta downward, F cos theta towards the right. So the force pushing it towards the right remains the same, which is F cos theta. But now F sin theta is downward, which for vertical equilibrium, mg plus F sin theta becomes the normal force, and friction force becomes mu s, and I am assuming the surface, the mu s is the same in both the cases. It is being pulled or pushed with the same force anyway in both the cases. So I'm sorry, this will become friction force limiting will be mu s into mg plus f sin theta. In the first case, it was mg minus f sin theta. This is equation 2. So since the normal force is more, the friction force acting also will be more, and therefore you will find it more difficult to push a trolley bag forward compared to when it is being pulled. Now let us take an illustrative example from one of the books recommended for JEE. And the question is, this is a 6 kg block. Which is being pulled with a force of 20 root 2 Newton making an angle 45 degree with the horizontal. So if I resolve 20 root 2 into f cos theta becomes 20 root 2 into cos 45, which is 20 Newton. F sin theta also is 20 Newton. So mg is 6 kg, therefore it is 60 Newton downwards, and normal force by the surface on the block is upward. So from what we have understood up till now, so since it is in vertical equilibrium, the normal force plus f sin theta, which is 20, becomes 60 Newton. So normal force now is 40 Newton. Coefficient of friction mu s given to us is 0.2. Coefficient of friction mu k is 0.1. So let us see if this mu s will be able to stop the relative motion. So F friction force static limiting becomes 0.2 into normal force, which is 8 Newton. 8 Newton towards the left is not going to stop this body from moving forward. So there is relative motion between the body and the surface in contact. So friction limiting fails. So you have been asked to find out the force of friction and the acceleration of the block. Now mu s has not been able to do its job. Friction has not been able to do its job. So what happens, as was discussed in the first video and illustrated in the second video, is mu k takes over. So there will be a friction force kinetic, which will become mu k into n, which will become 0.1 into 40, which will become 4 Newton. So instead of 8 Newton, you will have a friction force of 4 Newton acting towards the left. So the first answer is, what is the friction force? The friction force is 4 Newton towards the left. Second part of the question is, find the acceleration of the block. Net force is equal to mass of the body into acceleration of the body. So this becomes, what is the net force? 20 towards the right, 4 towards the left. So net force is 16. Mass of the body is 6 into acceleration. So acceleration becomes 16 by 6, which is 8 by 3 meter per second square. I hope I have made it clear. Please, if you like the video, don't fail to press on the subscribe button, and thank you for watching.